Hello, we're doing problem 1, question 1. Question 1 for chapters 23 to 24. So we're going to start off with part A. So for example, because we're going to be talking about electrical potential energy. And so what part A is first describing is pretty much we have a lead atom, lead nucleus right here, and around it we have our electron, which is at a certain distance. So we have our electron at a charge of negative 1.60 times 10 to the negative 19th coulomb, and our initial distance right now, because it's at rest, it's just right here, is at 1.00 times 10 to the negative 10th meters. This is our, right here is our lead, right here is our electron, and it's at a certain distance. And it's asking, so how much energy would it take, or at least how much work would it take to be able to move our electron over extra? Let me get a different pencil. So now we're moving it to a distance of 5.00 times 10 to the negative 10th meters. So we have our initial right here, and then our final. So the main thing that this is relating is that potential energy is equal to the constant of these two charges, initial and second, over R. Now, as well, work is equal to the energy minus the energy initial, and we can use this right here and pretty much implement our U in terms of both, and then factor out our R, so that pretty much it just looks like work is equal to our constant Q initial and second is multiplied by R initial and R final. Now this is essential equation right here will always kind of help us figure out what our work is. So either what our potential energy is, and the difference of that will then give us what our work is. Especially since we have these 2 points right here, it's going to demonstrate how we're going to get the total work for this as we're moving this electron right here to a final distance over here. So pretty much what we're going to do is then put in our numbers, and we're going to start by doing this outer part right here. So that's going to be our constant, we're going to times 10 to the 9th, 9.00 minus 1.60 times 10 to the negative 19, which is our initial charge, multiplied by, so the charge of the lead atom is going to be 1.31 times 10 to the negative 17 charge. So that's not going to be our second charge. That's positive. So that's going to be our first part right here. So we're just going to multiply this all together. Times 10 to the 9th times to 0, 10 to the negative 19 times 1.31 times 10 to the negative 17. So it's going to give us over here, it's all equal to negative 1.886 times 10 to the negative 26. So this is going to be constant, it's going to be joules per meter, because it's right here is newtons times Coulomb squared per meter squared. Alright, and then after we get our answer right here, we're then going to then solve for this section right here, which is our distances. So, we're at 1r initial, which is, our initial is 1.00 times 10 to negative 19 to negative 10 meters minus 1 over 5.0. So 0 times 10 to negative 10 meters. That should actually be switched around. At least should be different. Should be the final minus initial. Flip those on accident. Is RF minus RI. There we are. Alright. So we'll do those minus each other. This is going to be 1 over 5.0 times 10 to negative 10 minus 1 over 1.00 times 10 to the negative 10. So then this is going to be, move this back, just 1, 2, negative 8 to the 9th, which is negative 8.0 times 10 to the negative 9th meters. That's going to be what our answer is. So then we're just going to multiply all these things together right here. So since we solve for this section right here and this section right here, that means that the total work done is then equal to our previous negative 1.886 times 10 to the negative 26 joules per meter multiplied by negative 8 times 0, 0 times 10 to the negative 9th meter. And now since this is 1 over our radius, technically the meter would be, our meters would be to the negative 1. So it'd be almost as if it was 1 over meters. So that's how we are solving it. So that's how that will work when these two will cancel out, so that we're only left with energy, which would be in joules. So then negative 1.8, put these in parentheses, 6 times 10 to negative 26 multiplied by negative 8 times 10 to negative 9 is then going to give us the answer of 1.5. I'm going to round this over, so our total work will be 1.5 times 10 34. Right. 34 seems too low. There we go. Should be to the negative 16. Most likely just had something wrong. There we go. Total work is going to be 1.5 times 10 to the negative 16. So that would be the total work needed to be able to move this electron that's tied within this nucleus further to a final distance of 5 times 10 to the negative 10 meters. So that's for part A, which is pretty much the work to pull the electron outward. Now for part B, it's going to ask us if you release the electron from the position in A, what will be its kinetic energy when it's a distance 8 times 10 to the negative 12 meters from the center of the nucleus. So you can assume that the lead nucleus remains at rest since it's much more massive electron. So, if let's say, so right now we talked about the outward movement of the electron. If we release the electron from its position that it currently is in part A, so let's say the position that we had, which was at around the position given to us in part A, which is 1.00 times 10 to the negative 10 meters. If we release it from that position, what's going to be its kinetic energy as it moves? And when its distance as it's moved away is 8 times 10 to the negative 12 meters. So we'll be using the equation Ki. Let's actually first draw this out. What's going on? Pretty much we have our nucleus right here. And we have our original position of A, which is 1.00 times 10 to the negative 10 meters. And it's being released outwards to 8.00 times 10 to the negative 12 meters. Now this is almost as if it's actually, it seems to actually be closer. It's being released inwards. So if it's being held at, actually, this is what we should talk about, is that if it's released from this point that's in right now, we're at 1.00 times 10 to the negative 10 meters, and it's releasing it, it's moving inwards. Since this is positive, our electron will want to move inwards. It's now at 8.00 times 10 to the negative 12 meters. So it's been released from this position and it's wanting to move this way. We're going to have to use conservation of energy, or pretty much our kinetic plus our potential is equal to potential initial. So both our kinetic and potential initial are equal to our kinetic final plus our potential final. So pretty much this will be equal to, since our kinetic is at 0, because we are pretty much at the state of 0 right here of initial. So we're looking at 0 plus ui is then equal to our final plus uf. Because we're at this rest state, and then it's released. So then it's released, and we have just a initial potential energy. It's released, which is then equal to a kinetic final as it moves this way. So we're going to subtract this over our initial, because then to get our kinetic final, it's going to be the difference of our final potential minus our final initial potential. Now we know initial is going to be what we had previously. So we found our initial already in part A, which is going to be, so U initial is equal to negative 1.886 times 10 to the negative 26 meter, which is what our initial was. Now, we have to just get the energy itself over our time, or our distance. 1 times 10 to the negative 10 meters. So, and then do negative 1.86 times 10 to the negative 26. Close parenthesis. Then 1.20 times 10 to the negative 10. This then gives us negative 1. So our initial is then equal to negative 1.886 times 10 to the negative 16 joules. These will then cancel out. We're just left with joules. So to then figure this out, we're then going to have as well our U final, which will then be our energy again that we had previously found. So to the negative 26 joules per meter divided by then our current, our final movement, times 10 to the negative 12 meters. So then we'll then just change this to negative 12 and this right here to 8. So that then we're left with negative 2.357 times 10 to negative 15 final. So then K is then going to be equal to these subtracted to each other. Negative 1.886 times 10 to negative 10 meters minus the negative which will then turn positive of then this is not, it's going to be 16. We have 2.387 to negative 15. Which would then be 2.387, all in parentheses, times 10 to the negative 15 minus 2.387, not 1.886 times 10 to the negative 16. We're then going to be leaving us with K is equal to 2.19 or 2.20 times 10 to the negative 15 joules, which then that would be our final answer. So it's going to be the kinetic energy released from the released electron, and that's for part A and part B. So then moving on to part C and part D. Flip this around. Part C. Pretty much in a nuclear physics experiment, a proton with a mass of 1.67 times 10 to the negative 27 kilograms and a charge of E is equal to 1.60 times 10 to the negative 19 coulomb is fired directly at a target nucleus of unknown charge. You can treat both objects as point charges and assume that the nucleus remains at rest. So we have a proton. This is our proton. Proton pretty much is then 1.67 times 10, like 27 kilograms. And 1.60 times 10 to negative 19 cold. And that's our charge for this. So what it's going to be asking is, when it's far from its target, the proton has a speed of 2.5 or 2.5 times 10 to the 6 meters per second. The proton comes momentarily to rest at a distance of 5.29 times 10 to negative 13 meters from the center of the target nucleus. Then flies back in the direction from which it came. What is the electric potential energy of the proton in the nucleus when they are at 5.29 times 10 to negative 13 meters apart? So it shoots off starting at 2.5 times 10 to 6 meters per second. And there's a target nucleus remaining at rest somewhere over here. And it's approaching this nucleus. Now, it's moving there at around, let's say 5 points. So here will be our point of 5.29. 0.29 times 10 times 10 to the negative 13 meters. And our electron that's fired is then comes at rest right here, and then so it will fly towards this direction and then becomes flying back. So essentially, we have a positive electron or positive charged proton being fired towards a nucleus right here, which is most likely positively charged. Now we don't know the charge of the nucleus, but we can assume that as it's being shot forward at a fast speed, the repelling force of the other nucleus is then going to stop its speed, and then right here it reaches a rest point. This proton will then reach a rest point at a certain point, which was given to us as 5.29 times 10 to negative 13 meters away from the nucleus. Pretty much, once it finally gets to this point, is how it was able to finally slow down, as the forces were then able to slow it down. As it was being accelerated and shot this way, the force pushing it away slowed it down to right here at this point. And then, once it reached zero and rest, it's its maximum potential energy to then start shooting back the other way. So we have to figure out what is the electric potential energy of the proton and nucleus when they are at this point apart. Pretty much when they're this section apart. What is their potential energy, since this is at rest and this is also at rest? So what we're using for U is equal to, okay, we're still equal to our 1/2 squared. So pretty much our minimum distance potential energy will be equal to the kinetic energy, potential, which is then equal to 1/2 mv squared. So we know that our velocity is 2.5, so 2.5 times 10 to the 6 squared. 2.5 times 10. Put this in parentheses, 2.5 times 10 to the 6 squared. Whoops. Which will then be 6.25 times 10 is 12 meters per second squared, both squared, or meter squared, second squared. And then we're going to plug this back into our equation. So U is then equal to 1/2 v meter is 5.29 times 10 to the negative 13th meter, multiplied by what we got for our velocity, which is 6.25 times 10 to the 12th meters squared second squared. So we're then going to have pretty much our answer multiplied by 5.29 times 10 to the negative 13 multiplied by 1/2, which is then going to give us our answer right here. Did something off here. That's right, M is not that. Good thing to always remember is what the different M's are. Not working with meters, because you wouldn't multiply meters times meters. It is our mass, which we're multiplying against, which is 1.67, which is what was given to us. So our mass is 1.67 times 10 to the negative 27, which is a good catch. So yes, this right here, this equation, to re-go back, is 1/2 times mass times velocity, and that will give you kinetic energy, which is also equal to the potential energy. As it goes to this part, it's pretty much the potential energy. So this is not 5.29, but 1.67 times 10 to the negative 27 kilograms, which is our mass given. Now, when we put that together, that's going to give us that our potential energy is equal to 5.2 5.22 times 10 to the negative 15 joules. And then that works, because then that would be a mass times n squared, which then give us our joules. So then that's how we'll figure out what our potential energy is. But we also have part D, which is going to ask us, what is the charge of the target nucleus? So we have to figure out that part now. So we now know what our potential energy is. And we have our proton here. And they have a distance between them, 5.29 times 10 to the negative 13 meters. And then we have our other proton, our nucleus, which has a charge which we do not know. So we have a distance, and then we have potential energy between them. And we also have the initial charge that was given to us. So what we're going to do is pretty much to figure this out, is that what we can say is that potential energy is equal to K constant multiplied. Use our first equation that we used in part A, where the K constant multiplied by Q times Q over R, Q1, Q2. And pretty much we'll then substitute this, where our K constant is multiplied by Q1, we're going to say is E, which is our initial electron, which is given to us, multiplied by our big Q, which is this Q right here, which we don't know, over obviously R. So we then have to solve for Q, because we know what U is already. So what we can then do is simply just multiply. So we'll say U is equal to KE over R, multiply both sides by R. RU is equal to KEQ multiplied by pretty much our constant, our known electron on both sides. So our unknown charge is going to be equal to the pretty much distance times potential energy divided by the constant times known electron. So we'll write it over here, whole thing. Current to Q is then equal to 5.29 times 10 to the negative 13 meter, which is our distance, multiplied by 5.22 times 10 to the 15th, negative 15th joules, divided by our constant of 9 0 times 10 to the 9th means times meter squared or Coulomb squared, and then multiply that by our known electron, which is given to us, which is 1.6 times 10 to the negative 19 Coulomb. So we're going to input this all in the calculator and then figure out what is our unknown target charge. All right. So here I'm going to have two parentheses right there. 5.29 times 10 to the negative 13 times 5.22 times 10 to the negative 15 times pi negative 15. And then we have another double parenthesis, 9.00 times 10 to the 9th multiplied by 1.60 times 10 to the negative 19. And then that's going to be giving us. So our test charge, our target charge actually, is then going to be equal to 1.91 to round over 92 times 10 to the negative 18 Coulomb. And that's how you get the target charge. So then we're going to move on to the next problems. So then we have part E. So part E is saying 2 point charges are at a fixed position on the y-axis. So already we're going to want to start drawing ourselves a bit of a graph on the y-axis. So Q1 is a positive, and then at y0. So y0 Q1. And Q2 is a negative electron at y equals a. So y equals a something. So since it's negative, I put negative electron at y equals a. And then as well, so these are 2 electrons right here. Now, find the work you must do to bring a third charge, Q3 is equal to negative 3, from infinity to being at rest at y equals negative 2a. So it's the work to pretty much bring our third charge to rest with the rest of these guys right here. Now we have one that's positive, which is pretty much locking these two in together, and that's why they're at rest. So pretty much kind of fraction of them to it. So what we're going to be using is then we're going to be using our work is equal to constant Q. I'm going to start with Q3, so it's Q2 over R. It's R 3 to 1 plus, because we're pretty much from Q2, from Q3 to Q2, Q3, Q2, 3 to 1, plus our constant Q1, Q2, all over R 3 to 2. So this is kind of setting up the formula to put everything together, because we have to express these answers in constant, fundamental charge, and then the variable A. So we're not actually solving for a real answer here. We're more so figuring out what would we do to then be able to figure out what the work is. So we know that from R 3 to 1 is equal to 2A. Then from R 3 to 2 is equal to 3A. Because it's pretty much just saying that 3 to 1 is from negative 2A to 0. So negative 2A is equal to 0. Just equal them together, and then it will be 2A. And that's how that is from 2A. Now from 3 to 1, from 3 to 2, it's negative 2A to A. So if then we add it to the other side, it then equals to 3A plus 3A plus 2A. So that's why our distances are equal to those two. So we're then going to input what our charges are given. So we know that Q1 is equal to just positive E. And that Q2 is equal to a negative E. Same thing with Q3. Q3 is equal just to a negative electron or something. So work is then pretty much equal to the constant of K all over our negative E plus E multiplied together divided by 2A plus we had as well, which is K, which this time is going to be negative E. Or negative E over 3A. Now we can pretty much ignore our K's here as they would be outside the function. So pretty much be outside of it. So then pull it out, and we have negative E plus E 2A plus E 3A. And since our E's are pretty much very similar, these are multiplied together, so we're going to end up with a negative on this section. And it's just going to be negative A. Now these will just multiply into a positive. Now, we don't know what they'll multiply into, but it'll just be some E. So the charge times charge will just equal to just some charge that we know. But we just know that it's going to be negative. It's negative 2A, and this is going to be multiplied into a positive E over 3A. So from here, we can just take out our E's because we don't really need them. E is going to equal E no matter what. So we'll take it out, and then we're left with 1 over 2A plus 1 over 3A. And then A will always equal A. They can be taken out, so we have pretty much negative 1/2 plus 1/3. And as we're in it, then if we just add them together, it's just 1/4. That's 1/2 1/3. And this we turn into, we do -6/12 plus, let's do this, actually just do this by 6. Actually, I'll do it by 12s. So this would be then be 4/12, and this would be 6/12 negative, which is then equal to 2/12, which would be 1/6, which I'm doing that wrong. Why is it 1/4? It's 1/6. Yeah. If they are like terms, 1/12 will then be 3/6 plus 1/3, which would be 2/6, which is then equal to, subtract will then be 1/6. So our answer will then be 1/6 for these right here. So we know that work is then equal to K squared. Since those e's are multiplied together, it's e squared. Let me write that there. I forgot to include that. 2 e's multiplied together would just be e squared. K e squared over 6a. Multiplying it back into everything. And then pretty much converting our k into 1/4 pi initial. Then 4 times 6 turns into 24, so the answer is going to be equal to negative e squared over 24 pi e constant, because it wants a constant for e constant. Type wants the equation to be. And then that would be our answer for part E. A little complex because it is really talking about how, what variables are we going to be multiplying together to then be able to, if we just input everything into here, it would then give us our work, and that would be it right there. So that will be our final answer for part E. As it's the work that these two are then going to be all acting on effectively on each other. So then we're going to do part F, which should be tied to part E as well. The part F is find the total potential energy of a system of 3 changes. So pretty much we have a system right here. I'm going to fix this a little bit. And we're pretty much using the last setup that we had. Q1, 0. Q2 and A, and Q3, negative, positive, at negative 2A. These two charges are acting upon each other. Then we're going to have a charge acting upon these two, and then charge of these two acting upon each other. These two is pretty much, the distance is A. The distance here is 2A. The distance of these two is then 3A. So we're talking about the total energy of all the charges. So this is pretty much going to be the potential energy of U is equal to the energy that we have from 1 to 2, plus the energy that we have from 1 to 3, plus the energy that we have from 2 to 3. So all our different variations right here, the energies working against each other, is our total is going to be all those added together. So essentially we're going to be following relatively the same steps that we followed last time. And so if we have our energy 1 to 2, it's equal to our constant, okay, positive E times negative E, these two, negative E, pretty much at A, because that's our distance is in A, what we can then infer is that our distance, since what we did last time is we pretty much pulled all these out, and this multiplied together was just negative 1. Since we pulled all of these out, like how we did, and go out the 1/2 and the 1/3, A, since it has no 2 or 3, it's just 1. It's just 1 over 1, negative 1. Since these two multiplied together would be E squared or negative E squared. And we would just multiply that out to then be able to get this. So we're going to work with this within the same principle. Since our total is all of them together, and we figured out what 1 to 3 is and 2 to 3 is already in our previous problems, 1/2 and 1/3 was, that means that we just have to do is just 1/2 negative, so negative 1 minus 1/2 plus 1/3 is then equal to our total distance-wise. So if we all do this, that's pretty much 6 over 6 minus 3 over 6 plus 2 over 6. This is then just 1 over 6. 1 over 6 plus 6 over 6 would then just equal to negative 7 over 6. And then that's what we would get. So pretty much how we had 1/6 and multiplied it times our constant k, which is 1 over 4 pi e to 0. The 6 and 4 will multiply together. The 7 and 1 will multiply together. So we'll have a very similar answer to part E, which is then just going to be negative 7e squared 24 pi epsilon constant day. And that's our answer right there. So now let's move on to part G. Part G. We have a point charge of Q1, so a positive Q1, which is equal to 5 nanocoulomb. It's at a fixed position of pretty much x is equals 0, y is equal to 0, z is equal to 0, so it's at 0. It's at the origin. And you find that you must do 8.10 times 10 to the negative 6 joules of work to bring a second point charge from infinity to position x is equal to plus 4 centimeters, y is equal to 0, and z is equal to 0. What is the value of the second charge? So we have our energy given to us, and we have our charge given to us. We have a negative point charge right here, which is pretty much what we're doing is bringing it, its position, being somewhere in the world, to then being locked in. Since there's no change in our y or a z for anything, we're going to be on our x-axis. So this to then be 4.00 centimeters. So this is our origin right here, 0, 0, 0, 4.000. This right here is then to here. It's being locked in at this point right here. We need to figure out what is the value of the second charge. So we know the energy to bring it to this point. What is its value? So pretty much we have work is equal to 8.10 times 10 to the negative 6 joules. Our distance is is going to be equal to, let's put this, it's 4.00 centimeters. Put it in meters, which is then equal to 0.0400 meters. And our Q1, which is right here. So what this would then be, we know that work, since work is also equal to U, it's then also equal to our problem where it is the constant of Q1 times Q2 over R. And we're just going to solve for Q2, very simply, as we've done with other problems. So what we pretty much do, multiply R on both sides and then divide by the constant Q. So our energy, so second charge is equal to our potential energy, or our work, multiplied by our distance, and then divided by the constant and Q1. So let's get this charge going. Q2 is then equal to 8.10 times 10 to the negative 6 joules multiplied by 0.04 meters under 9.00 times 10 to the 9th meters squared over coulomb squared multiplied by Q1, which Q1 was 5 times 10 to the negative 9th coulomb. So we'll then just input all these values together. So I have our double parenthesis of 8.10 times 10 to the negative 6 times 0.04. Make sure our parentheses there. And then as well, then we have 9.00 times, not that, 10 to the 9th times 5 times 10 to the negative 9. And that's going to give us a charge of Q2 is equal to 7.2 nanocoulombs, because it's to the negative 9th. So to the negative 9th, we'll just put that as nanocoulombs. And that's our Q2 charge right there for part G. So we can move on to part H. In part H, pretty much says, once second charge is in place, how much additional work would you have to do to bring in a third charge? So, do this a little smaller, but we have charge here, both sitting on the same axis and just only 4 centimeters. Now, how much energy, how much work would it have to do to then bring in another point, the charge of 2.00 nanocoulomb? Now this time, it is a positive charge right here. Now it's not on X or Z, but it's down, and Y equals 3.00. Actually, shouldn't be down, it will be up, but flip this around, essentially. This would be above this. So we have really is a triangle charges where we have Q3 right here, Q1 right here, and Q2 right there. That's essentially what's working here. We have a distance of 4.00, and then this would be distance of 2.00. So we can figure out what our hypotenuse is right here. Because what we are going to need is pretty much the energy of them added together. is 3, not 2. Let me just make sure I'm getting my diagram good. 3.00 centimeters. And then 3 squared plus 4 squared is 9 plus 16 equal to 25, which is equal to 5. Let me square root it. So then this is going to be 5 right here for the distance. So it's pretty much work is equal to our constant of k multiplied by q, charge of 3 multiplied by the distance of q 2 from 3 to 1, or 3 to 1 plus q 2 from r of 3 to 2. Essentially what we're doing here is just we're multiplying, we're taking kind of work is equal to q times q, the constant, divided by r, and we're taking the q and the r over here and making them part as themselves, since we have two different distances right here and they're all acting upon each other. And we're doing this with q2, which we found. So we're doing it from the distance from 3 to 1. So this charge 3 to 1, then this charge from 3 to 2. So first we're going to find what k, q3 are right here. And that's going to be 9.00 times 10 to the 9th multiplied by 2.00 coulomb, which is going to be 2.00 times 10 to the negative 9. Well, that gives you a really easy number, which is nice, which is then 18. And this is all then going to be multiplied by originally, which is then going to be our first charge with our distance, which is pretty much 0.03. This is our distance right here, plus our second charge, 0.2, times 10 to the negative 9, coulomb, over our distance from 0.05 meters. I'm going to just simply put our final answer right over here, because essentially it's going to be parentheses. Actually, do that. Parentheses, which was our initial 5.00 times 10 to the negative 9 over 0.03, which is the distance of the two together, plus then the second charge is 7 times 10 to the 10 to the negative 9 as well, with a distance of 0.05. Oh, I did something wrong. I probably, yeah, right there. I added those two. There we go. Which is then going to equal to 3.1. Say 3.11 times 10 to the negative 7. And we're going to multiply that answer by 18, which is what we got. Multiplied by 18, which was the constant, times our third charge. And then that's going to give us our final answer. So work is then equal to 5.59 times 10 to the 6 joules. And that's the work needed to be able to introduce another third charge of that charge of 2.00 nanocoulomb. Because essentially we're just bringing in a third one and it's being locked in with the other charges. And that will be everything. So thank you very much.